Welcome everyone to NSTA Web Seminars, where you can find live interactive learning at your desktop. Tonight's presentation is part of our series on the Next Generation Science Standards, Cross-Cutting Concepts, and we'll be looking at patterns. Our presenter this evening is Kristin Gunckel. We also have Ted Willard online with us to provide some information on the Next Generation Science Standards. My name is Bryn Slate. I will be moderating, and we have Jeff Lehman online with us to provide technical support. Before we get started, I wanted to remind everyone to visit the NSTA Learning Center, your online portal for over 10,500 resources for science educators. And we've been adding new resources all the time to the Learning Center. You'll see that over 3,600 of those are free. You can add them to your My Library area to access when it's convenient for you. Our community forums are a great place to have discussions with other science teachers, and our online advisors are available via the live support button to help you find what you're looking for there in the Learning Center. We also have free tools that you can check out to help organize your learning and reach your goals and document what you've done. It's all available by going to learningcenter.nsta.org. And now I'd like to introduce today's presenters. First, we'll have Ted Willard, who's with the National Science Teachers Association. He'll be providing some expertise on the Next Generation Science Standards. And our featured presenter will be Kristin Gunckel from the University of Arizona. And I'll go ahead and turn it over to Ted. Welcome, Ted.
Thanks, Bryn. Thanks, everyone, for being here tonight. I'm really excited to do this. This is a sort of a starting the spring season, the spring semester, we could say, of these web seminars around the Next Generation Science Standards. We're onto a new area to work with. We're dealing with the cross-cutting concepts now after doing a whole number of pieces around the scientific and engineering practices. But to take just a quick step back and give you a little bit of a sense of how the standards came to be, I want to note first off that we've got 4 organizations that have played a key role in doing these: the National Academies, Achieve, NSTA, and the American Association for the Advancement of Science. And there's been essentially a 2-step process in here. We have the development of a framework for K-12 science education, which the Academies came out in July 2011. And then the standards themselves, which are being worked on by a group of states under the coordination of Achieve. And it's from these standards here that we will be seeing assessments being developed, curricula being developed, plans for instruction being focused and produced, and teacher professional development focused on as well. And so starting off with the framework itself, I want to give you a little bit of a sense of the pieces of it. First of all, the 3 dimensions of the framework. If you haven't heard, you'll hear again and again, I'm sure. The scientific and engineering practices, the cross-cutting concepts, and disciplinary core ideas. If you haven't had a chance to look at the framework, I strongly suggest that you get a copy and read through it. If you read through it once, I suggest you read through it again. It really has a lot to offer. You can get a free PDF from the National Academies Press going there, or you can get a hard copy from NSTA Press at the NSTA store. So these are the scientific and engineering practices listed here, and as Bryn referenced earlier, as we've talked about before, there are web seminars focusing on each of these 8 practices that went through in the fall. And as well as some things that talk about them to get all together since the first of the year. We're now in a series that's going to focus on the cross-cutting concepts, and tonight we'll focus on patterns. Cross-cutting concepts are different a number of ways from the practices, in that although the practices are sort of all designed to be used together, each cross-cutting concept sort of fits as its own way of thinking about how life, earth, and physical science have some connections, have some similarities in what they involve and engage in. And probably, I think a lot of people who've been doing work around the the standards have said the cross-cutting concepts are in some ways the hardest to sort of figure out what to do with. And so I think we're all going to be very interested to hear what Kristin has to say tonight and what some of our future pieces are focusing on. Finally, the third dimension of the standards is the disciplinary core ideas, life, physical, earth and space science, and then also engineering and technology is considered one of the core ideas. And of course, each of those core ideas can be farther broken down into different pieces, which are broken down even farther to a sort of outline and then down to very specific learning goals. So as I've said, this is the process we've got. We've got the framework, and that leads into the writing of the standards themselves. Each of the states that's in blue here has been one of the 26 states participating in the development of standards along with a group of 40-some-odd writers. If your state's in blue, your state has promised to give strong consideration to adopting these standards when they're done, and they're expected to be finished later this fall. I should also point out, though, if you're in one of the gray states here, those states also will have the option, once the standards are completed, of choosing to adopt. They just aren't as involved in the writing of them. So here's an example of one of the standards, one of the pieces all together here. You have a performance expectation up here, and this is designed to guide assessment around these standards. It's not necessarily the most important thing in terms of thinking about teaching and learning, but that assessment piece is meant to focus on the scientific and engineering practice, the disciplinary core ideas, and the cross-cutting concepts. So for example here, develop molecular models of reactants and products to support the explanation that atoms and therefore mass are conserved in a chemical reaction. That fun part, develop molecular models to support the explanation, is working with the practice. The text in orange here, though, is core ideas, that reactants and products, or the atoms and therefore mass, are conserved in a chemical reaction. And this idea of conservation is a cross-cutting concept, that matter is conserved because of atoms. And so those three different elements link together to work at this. And even as this is the assessment, as we think about taking the material in the foundation box, in this lower box right here, these different pieces, and working together, we want to think about how instruction can focus on combining practice, core idea, and cross-cutting concepts. And so to look at that, to look at an example of the cross-cutting concepts of patterns, we're going to pass things on now to Kristin to talk about. Thank you, Kristin. Take it away.
Hi, welcome everybody. I'm glad that you're interested in learning about patterns today. I want to give you a little bit of background, my background. I am an assistant professor of science education at the University of Arizona, where I teach the science methods course for our elementary pre-service teacher program. And I also teach graduate courses in science education. I got my PhD in science education from Michigan State University, and I conduct research in science teacher education and supporting teachers in teaching science. Before I was at Michigan State, I was a middle school science teacher, and before that I was an environmental educator working for a museum. So I have both formal and informal teaching experience. And I also have degrees in geology, and when I was teaching middle school, my focus was on earth science. So that gives you a little bit of a sense of where I'm coming from. Let's see, I think I skipped something. Right, so just a few qualifications for today. Much of what I'm talking about today are things that I've learned from other people. So there's a lot of people who've been thinking hard about patterns and cross-cutting concepts, and so the ideas that I'm presenting today are across a wide range of people. And I use what I've learned from other people to help teachers think about supporting their own students in learning science is science. So just wanted to say that. Here's a little bit about what's ahead. We're going to talk a little bit about what patterns have to do with science, and then think about why we want our students to learn about patterns in school, in learning school science. I want to take a little bit of time to think about what learning about patterns looks like in the next generation science standards, and then we'll think about what that looks like in the classroom. So let's start with getting a little bit of feedback from you about what you're thinking about and your comfort level with this whole idea of patterns.
Okay, thanks, Kristin. First, what we're going to do, folks, is I'll make your screen marking tools active once again so that you can select a piece of clip art to place in the appropriate column. You can check out the labels there and find the one that makes the most sense for you. And this is at the start of our web seminar on patterns, so we know that you might be in that far left-hand column, which is just fine. And we hope to provide some information that will move you along the spectrum tonight. For those who joined us after we practiced our clip art in the introduction, it's located on the screen marking toolbar, which is adjacent to your participants window. It's the bottom button there, and you'll select common symbols. And Kristin, it looks like we've got people in all boxes here and ready to learn about patterns with you.
Yeah, this is nice to see. We've got people across the whole range, and I'm hoping that everybody finds something in today's presentation that helps them move across the boxes. So with that in mind, I'm also interested in what you're hoping to learn today. This is the first seminar in the cross-cutting concepts, and I'm interested in finding out what brought you to this seminar today and what you hope to get out of it.
So what we're going to do for this one, everyone, is we will take responses from everyone in the chat window, but we'd also like to get some featured responses on the table there. So if you'd like to take a stab at sharing your learning goals for today, you can use the raise hand button, and I'll give you the tools to use your text box function to type on the screen. All right, and I'll go in order here. So Anashri, you will now get the tools, so you can type in box 1. Mina, you've got box 2 there. Glenda, box 3. And Hubert, thanks, you'll take box 4. And Bernadine and Mike, thanks for volunteering. We'll get you on the next one. You can feel free to type in the chat window to share your responses. But for those who have the screen marking tools, go ahead and use your text box tool, which is the 4th one down. It's the one with the A on it and some lines next to it. You'll use that text box tool to type your response there in the table. And if you're having trouble with that, you can just feel free to type in the chat. And Kristin, it looks like we've got some great ideas flowing into the chat window as well, while we're waiting on a couple of ideas into the screen as well. Kristin, I think we may have lost you. I see your mic is on, but I'm not. Oh, go ahead.
Yeah, I'm still here. I was if there were other people who were going to
Perfect. Yeah.
type in, but I think I was reading a lot of the ones that are coming up on the chat. And so I'm seeing a lot of people who are interested in learning about what patterns are and how to think about them in their classroom. And so these are all things that we will talk about today.
That's great. And for the folks who it looks like maybe having some trouble with that text box tool, go ahead and type in the chat window, and then we'll move on. But I appreciate Vinashri's response on box 1. Thanks for being willing to share that front and center there. And I think it sounds like it's a good representation of the audience this evening wanting to find out some strategies for applying there in the classroom and helping students understand how to take advantage of these ideas.
Great. Looks like we got one more that's coming in. All right. Thank you, everybody. Yeah, so I want to learn about helping students understand and see patterns across different disciplines and how to integrate different core ideas. I think we'll definitely touch on that today. And in the third box, I want to understand the correct usage of patterns in relation to practices, core ideas, and other concepts. And I think hopefully we'll touch on that today, and you'll feel like, I hope that you feel like you reached your own learning goals for today's presentation. So the first part is, what do patterns have to do with science? When you think about science, in many ways it's about explaining observed patterns. Patterns gets right down to the core of what science is about. This is a representation that you may have seen before if you attended some of the seminars last fall. It also showed up in Christina Schwartz and Cindy Passmore's presentation on models. They labeled it a little bit differently. They called it the observations, patterns, and models triangle, and I call it the experience, patterns, and explanations triangle. And if you look at the triangle, you see that we have the base. What holds up science are millions and millions of experiences with phenomena. I use the word experience broadly because it includes thinking about observations, but it also lets us think a little bit about how students, especially elementary students, observations and experiences with natural phenomena are broadly defined. But when we think about science of science, we can think about these experiences, label them with more maybe scientifically familiar terms such as data or observation. But when we think about science, we've got lots and lots of scientists working on lots of different interesting problems, and their experiences collectively come out to a very large pool of experiences. Looking across those experiences, we can start to recognize some patterns in the data. And they're represented in science by such things as laws like Newton's laws of motion, generalizations. We can represent them with graphs and charts. But it takes these millions of experiences and distills them down into a set of patterns that we can more easily deal with. And then we, in science, look for models, theories, explanations to come up with these ideas that help us explain these patterns. So as we move up the triangle, we find that we narrow down the ideas and sort of put them into boxes that we can handle and wrap our head around. As you move up this side of the triangle, this is where we think about inquiry, where we're learning from experiences. So scientists and students are always learning from experiences. And then we can go down the other side and we can take our ideas, our explanations, models, theories, and we can apply them. We can use them to understand new patterns that we might see in new experiences. So we'll be using this triangle today to help us think about patterns as we take a look at how scientists think about patterns and really the role that patterns play in helping us develop the theories and models and explanations that are at the top of this triangle. So let's take an example. One example that I like to use and talk about is developing the theory of plate tectonics. One pattern that people have noticed for a long time, since we've had maps that have been detailed enough for us to really see continents, is this peculiarity that it seems like there's an apparent fit between some continents, as if they were big pieces of the puzzle. This is something we've noticed for a long time, and this is an example of a pattern. And we can combine it with some other patterns that people have noticed over time. Geologists have noticed that the rocks of mountain ranges match across continents. For example, the Appalachian Mountains in North America match in rock type and age with the Caledonian Range in England and also the Atlas Range in Western Africa. Same with some rocks down in southern Africa, the Cape Fold Mountains, the match in age and type with rocks and mountains in South America. So lots and lots of people made observations in order to be able to see this pattern. So if we think back to the triangle, this particular pattern is based on probably millions of single observations. Another pattern people have really noticed is that there are matching fossil records across continents. This pattern, again, is based on millions of individual observations. As paleontologists have described fossils and then mapped their locations to notice how their distributions seem to line up across continents. Some of the ones you may have heard of before are the Mesosaurus, which was a freshwater reptile, or the Glossopteris, which was sort of like a fernish type plant. That has shown up in fossils in Antarctica, Australia, Africa, South America. And then another kind of pattern that we've noticed across continents is glacial striations that match in time. These striations indicated a massive ice sheet that was present in continents about the same time, and these continents now, when you think about them, are many of them distant from the South Pole, like India or parts of Africa. So there's all of these sort of patterns. When we start looking across them, are really very intriguing. So based on these millions of observations, which can kind of be reduced to these handful of patterns, Alfred Wegener in the 1920s proposed the idea of continental drift to explain these patterns. His idea was that the continents had once been assembled together in this supercontinent that we called Pangaea, and the idea explained why the continental margins might fit together, how mountain ranges, fossil occurrences, and climates could match across continents. There was one problem, however, and that was that his ideas didn't have a mechanism. Nobody could really think about or wrap their head around how continents could move around the globe. And so initially his ideas were rejected, although they weren't totally discarded. It was still kind of this intriguing idea that was sitting out there for a while. So then we had some more patterns that emerged across the last 50 years as technology enabled us to measure things like earthquake locations and map those onto the globe. And we started to notice that volcanoes and earthquakes wind up along edges of what we now call the plate boundaries. Another pattern that we noticed as a result of World War II with the invention of sonar and the mapping of the seafloor was that the age of the ocean crust gets older as you move away from sort of a central axis. So if we look here where we have this red, which is the youngest crust, and it goes right down the middle of the Atlantic Ocean, and the older oceanic crust is along the edges of the basins. This led to a new idea about seafloor spreading, which when we combined it with continental drift, we were able to begin to see some possibilities for explaining how continents could move in all the patterns that we've seen. Just one more pattern that supports this idea is the idea that rocks, when they are igneous rocks, when they're molten, the magnetic minerals line up with the location of the magnetic pole at the time that the rocks are molten. And then they solidify, and that magnetic orientation is locked into the rocks. And when we draw them out on a map, we end up seeing that rocks at different continents have similar pattern, although they don't match in location exactly. But if we rotate the continents backwards, we end up seeing that these two patterns actually end up matching. So all of this evidence supported this new idea of plate tectonics. And it provided us with a mechanism, mantle convection, that could account for all of these patterns. And as you all are very familiar with, plate tectonics, according to this idea, the crust is broken into small plates. The oceans are denser and thinner than the continental plates, and convection in the mantle drags the plates around the globe, causing them to break apart, collide, producing earthquakes and volcanoes along the edges. And so now we have an explanation for all of the patterns that we have seen. And so we can kind of put this together into what I call an EPE table, which is a way of thinking about experiences, patterns, and explanations, and the relationships among those three. So we start off with millions of observations made over at least 50, probably more than that, years by thousands of people. And we come up with a limited number of patterns, and then develop an explanation that can account for those patterns. We can test those explanations to see if they hold up to new observations. But this is really the process of scientific inquiry, and patterns are what hold the experiences and the explanations together. And then we can go back the other way with application and use our ideas, our explanations, models, theories to explain new patterns that we might notice, like locations and types of volcanoes or mountain ranges, mineral deposits, Again, lots of experiences that thousands of people have over many years. So patterns are important for across all disciplines of science, not just earth science. When we look across science, we see that there are patterns and the types of patterns that we see and that are useful in science. Each of these types of patterns helps us organize our observations, recognize categories, notice relationships, and see changes. And we can use many tools to help us see these patterns, such as graphs, charts, maps, and statistics. So I have just a couple of examples of things that maybe you might not have thought about as patterns before. Classification is a way of finding patterns in experiences. It helps us organize our observations. It helps us see relationships among objects or experiences that are similar or different. And classification is important in all the branches of science. We can classify organisms, rocks and minerals, elements, clouds, types of galaxies, and I suppose even patterns. We can classify patterns. Looking at how phenomena are distributed is another way to find patterns. In earth science and ecology, for example, we rely on maps to show us distributions. In all branches of science, we can rely on statistics to help us see how individual observations are distributed in comparison to other observations of the same phenomena. We use normal curves, and we can calculate means and standard deviations and errors to help us analyze the relationships of one observation to another. Another type of relationship, or another type of pattern are relationships. Graphs help us see relationships between variables. So, for example, in this one we see a relationship between car mileage or vehicle mileage and vehicle weight. And we can see a negative relationship here in these points. That is, vehicle weight increases, mileage decreases. And then patterns also help us see change, changes that we might not otherwise notice. Graphs are important tools for helping us look for changes. We can figure out rates of change, identify patterns in changes such as cycles or periodicity in cycles, or we can see anomalies in data. So many of you may recognize this graph of change, change in the carbon dioxide in our atmosphere. It's known as the Keeling curve. And it also shows a cyclical relationship across the year, cyclical changes in the amount of carbon dioxide in the atmosphere related to the seasons. So these are just to give you an example or give you some tools for thinking about patterns in science. And so I thought maybe we could take a few minutes to reflect back on this before we move on. I want to give everybody a chance to think about what we've talked about so far, and maybe people can type into the chat some of their ideas about what we just talked about. What are some examples of patterns you use in your teaching? And what are some other types of patterns you can think of besides the ones that I showed as examples? And do you have any particular questions about the role of patterns in science?
Great, and I can see we're getting some people already putting in some pieces here. I can see you mentioning just the pattern and multiplication tables, moon phases, the rock cycle, dichotomic keys, plant growth, indicators for acids and base, the periodic table, weather patterns, life cycles. These are the pieces that folks are mentioning here. Kristin, seasons. What are your thoughts about the ones that are being listed here, Kristin?
I think these are all excellent examples, and we can see that once we start thinking about it, patterns are everywhere in the content that we're teaching and in the science that we are investigating. I'm also noticing here how these patterns that people are putting in come from all of the content areas. So we're seeing earth science, life science, physical science.
Absolutely. Folks, I want to make sure you're free. There's an opportunity. We can also now ask Kristin specific questions if you have some for her. As an astronomy person, I like the Kepler's law example that just was put up here. And was just noticing, it's not quite on time with Kepler, but noticed on Google today that it's Nicholas Copernicus's birthday, I believe. So I'm going to spell this name wrong, or pronounce this name wrong. Vanishri has asked, how can we assess students' understanding of patterns?
I think that's an excellent question. I think a lot of the assessment of patterns comes, we'll talk about this more later when we get to looking at some specific examples of performance expectations at least in the draft of the standards that we have. But the way that the practices and the disciplinary core ideas and cross-cutting concepts are intertwined, I think that as we're assessing the performance expectations, students' understanding of patterns and their role in science will be reflected.
Yeah, I think that makes a great deal of sense. I know one thing when I was a teacher is just the tendency of students, for the proclivity to try to look for patterns, to be searching out for something like that was something when I saw students doing that, I was very pleased about.
I think also engaging students in finding patterns and making graphs or making representations of the type of experiences that they're having in the classroom really can help you see what patterns they're noticing, and then if they can talk about those patterns, explain them, or make arguments about them. And we'll talk about that a little bit more in the next section.
Got one more question here. The framework says that cross-cutting concepts should not be considered additional content. How do you see that working out in the classroom?
Right, I see that again as in the way that they're linked with the practices and the core content. So when you think about having students construct explanations, for example, if the cross-cutting concept of patterns really is there to support students in constructing explanations. What are you constructing the explanation about? And by recognizing patterns, we can help students understand what they're explaining. Same with modeling or engaging in argumentation. Students are using patterns to support the arguments that they are making in the classroom.
Great. Well, why don't we move on here a little bit, and then let's try to take some more questions later on in the presentation.
Okay. So this is a poll slide on thinking about how you use patterns and how your students encounter and think about patterns in your classroom.
Thanks, Kristin. Everyone, your poll buttons are now active, so you can go ahead and select the best response for you and let us know what you think about patterns in your class. For those of you who may have joined us a little bit late, the poll buttons are located right under your own name at the top of the participants window. And you can go ahead and select your response there. We'll give a moment for everybody to give a response. And I understand that some folks with us tonight are outside of the classroom, so may not have quite a appropriate response on this list. So if that's the case, you can feel free to type in the chat if there's something that falls outside of what makes most sense for you. But it looks like most of you have been able to pick a letter. So we'll go ahead and lock our poll so that we can take a look at the total responses here and publish our graph up on the whiteboard. And Kristin, it looks like most folks are in category A, and we've got some B, C, and D as well.
That's excellent. I think seeing the spread helps us get a sense of where people are. I think I saw one comment on the chat that students are used to looking for patterns in data or experiences, and I think that since we've really been, since the last National Science Education Standards, we've been really emphasizing inquiry and having students engaged in looking at data, looking at having experiences in science is really, we've really brought a lot more of the patterns into the classroom. I think, when I think about what we want students to learn about in science, I would add to that we want our students to, that learning about patterns helps our students to also understand the nature of science and where these explanations and models that they're learning about come from. The same way that the example that I just gave you at the beginning with plate tectonics, when we help students understand the patterns that support that idea, they begin to get an idea of how science works. The cross-cutting concept of patterns also helps us really engage students in the scientific practices so that they are constructing models and engaging in constructing explanations or making arguments. It also helps our students understand and be able to use scientific explanations, models, and theories. So if you think back to the triangle, the right-hand side of the triangle is application, and making patterns something that students are always thinking about. It helps them recognize and maybe apply the scientific ideas that they're learning about, so they really become tools for helping them understand the world around them. And then I put down here at the bottom in parentheses, because I'm not sure that it's really emphasized in the NGSS, but I think patterns also help us really develop an aesthetic appreciation for science. Some of the patterns that we see are really very beautiful or awe-inspiring, and just recognizing patterns is, and the aesthetic appeal of them, I think, is an important aspect of appreciating science. So let's look closely at the patterns, the way patterns are talked about and represented in the next generation science standards. Patterns are incorporated with the scientific practices and the disciplinary core content, and Ted talked a little bit about that at the beginning. Patterns are also represented across the disciplinary strands, and then there's a progression of ideas about patterns across the grade bands. So I want to talk a little bit about each of these things. I want to give you some examples from the most recent draft of the Next Generation Science Standards. I want to emphasize, though, that the draft that came out in January was still a draft, and they took a lot of comments and are considering the feedback that they got. So what I'm showing you today might not be the exact wording of the pattern concepts or the performance expectations, but we can get a real sense of what it's going to look like from the examples in the draft. So on the left is an example of a pattern cross-cutting concept from the Next Generation Science Standards, so that's why it's in green, since that's kind of the color coding that the NGSS uses. And on the right is a performance expectation that is linked to this pattern in middle school from physical science. So patterns in rates of change and other numerical relationships can provide information about natural and human design systems. And when we look at this performance expectation, we can see how comparing simple molecules helps students kind of begin to see a pattern at the molecular level about how natural systems, systems, or if we're thinking about engineering, human design systems. This same pattern shows up in life science, constructing explanations about common patterns of interaction within different ecosystems. Again, allows us to think about and understand relationships within natural systems. And then again, this same pattern concept shows up in earth science. All of these are middle school examples, analyzing maps or graphical displays of data to assess likelihood and possible location of future severe weather events. Again, helping us understand natural systems. So this is, I think, really illustrates the ways in which these pattern ideas are represented across the disciplines, cross-cut the topics that we teach in school. Across grade bands, there is a progression of ideas about patterns. In the early grades, students are mostly working on pattern recognition, so sorting, looking for similarities and differences among items, usually items that they can touch and feel and see. As they move into the upper elementary grades, classification becomes more important. So not only sorting, but recognizing and putting things into groups, and the reason why items are in specific groups or phenomena or objects. And also beginning to think about rates of change. As students move into the middle grades, now we can start looking at patterns across scales, especially getting down to the microscopic and atomic scales. Relationships become important, especially being able to use patterns to identify cause and effect relationships. And using graphs, noticing patterns in using charts becomes a focus. And then finally, when they get into high school, students are really expanding across scales, observing and recognizing patterns not only at the microscopic and atomic scales, but also landscape scales, or even larger when we think about the solar system and the universe. So recognizing that patterns look differently across scales, and sometimes we have to go to different scales to see these patterns. So I want to give us a chance to get a little bit more thinking time about what we've just talked about. I'm interested in what's new here for you, if anything. Maybe it's not new. And how thinking about pattern cross-cutting concepts helps you think about the content cutting across disciplines and grade levels. And then any questions that you have.
Okay, Kristin, there's already been a little bit of discussion here, some interest about patterns and how they fit in the difference between relationships and patterns, and seeing how patterns could be a more broadly applied term, if I'm reading what folks are saying here. Also some interest in some sort of kind of keeping track about aspects about patterns as a cross-cutting concept versus cause and effect. But we've got a first question here about how do patterns look similar or different for science and a component of practices and engineering practices. I think what they're pointing to here is you can talk about patterns in science and you can talk about patterns within engineering, and are they dealt with pretty much the same, or in what ways are they maybe dealt with differently between those two activities?
So I think that when you think about what engineers are doing, a lot of times they're really on that right-hand side of the triangle I showed at the beginning, where they're applying ideas in science to create new systems and new things for us to use. Patterns really become important for them in being able to sort of predict what might happen with whatever they're designing, and also to be able to consider the constraints under which they are designing their system. So patterns really help them, I think about the world in which they are designing. And so to me it's kind of science is going up the inquiry side of the triangle, and engineering is coming down the application side, and the patterns really is the kind of glue that holds the experiences and explanations together for both scientists and engineers.
Okay, great. We've got Anne bringing up this point about patterns, identify correlation, but correlation is different from causation. So how do we students understand the difference between there's a pattern between two things and that there is a cause and effect between those two things?
Yeah, I think that the NGSS treats that by having another cross-cutting concept on cause and effect. This is one place where maybe there is a link between two of the cross-cutting concepts, in that you have to be able to see patterns in order to recognize cause and effect and then maybe explain those. I think it is important that our students understand that just because there's a pattern doesn't necessarily mean cause and a causal relationship. And so we do use other tools, especially from statistics, to help us think about the causal relationships that might be present in the patterns. So I think the patterns is much more general. Correlations fit broadly within patterns, and cause and effect is one type of pattern or one type of relationship that patterns help us.
One thing that always helped me in thinking about pattern causation versus correlation and these outlets ties right into your first example today when you talked about continental drift and the ideas of matching things together, and what ultimately led to the theory of plate tectonics, and how the fact that there wasn't a mechanism in place at first gave suspicion about whether the pattern meant something really. And so that aspect of identifying a mechanism is one of the things that really leads you into shifting from just a correlation into seeing some cause and effect. But I'm interested to see what one of our later presentations talking specifically at Cost Effect says about that. Let's see here. We've got here's a little sort of a concrete piece here that maybe you've got some ideas about. Do you have any ideas about things that students in grades 3 through 5 might be able to do that would deal with rates of change?
Yeah, so I think in the elementary grades, thinking about relative speeds, for example, faster or slower, helping students think about cars speeding up or cars slowing down or other objects speeding up or slowing down. That might be a physical science example. I think in life science, we could think about how things change across that, for example, a human's life cycle is across decades, where an insect's life cycle happens over days. And students can kind of see how things change quickly or change slowly without having to get into lots of physics to explain that. They can start to see that things change and they don't always all change the same rate.
That sounds great. I thought I had one more up here. Let me see if I can locate it again. I just scrolled through so many. Do I hit that one? I think. If I have the other one here, I don't see it right now. So why don't we move through to the final pieces we've got, and we can then close up at the end here.
Okay. Oops, let me go back. So I want to spend the last part here thinking about what does this really look like when we're thinking about planning and teaching science. If you think kind of at what traditional school science looks like, and I'm not saying that any of us here are necessarily traditional teachers, but when we think about kind of the way that science historically has maybe been taught, there's been a heavy emphasis on explanations, with some experiences usually provided to confirm or prove those explanations. And the patterns that emerge from those experiences are often hidden, partly because, as you can see, the triangle is turned upside down, and there are fewer experiences that students either have or have access to or are able to learn about. And so they don't really see how the experiences hold up the explanations that they're learning about. The patterns really aren't there and aren't visible. Whereas the kind of science that I think the NGSS really is emphasizing, patterns are explicit. We want students to see that connection between the experiences and the explanations. We want to really show students, engage students in finding those patterns. I often emphasize to my pre-service teachers that in order to do this, we really need to provide our students with experiences, either actual hands-on experiences or virtual experiences, or looking even at data. They may not have been the ones who collected the data, but looking at the data to see these patterns and then incorporate those patterns into the practices, analyzing data for patterns, constructing explanations to account for patterns, or engaging in arguments about the patterns. So we really, in contrast to the upside down triangle, are trying to emphasize the role that patterns plays in linking the experiences and the explanations. So really I think that teaching about patterns in this way is something that many of us are already doing and maybe haven't really thought about as much the way that we maybe are emphasizing patterns. So this is just to help us think about where patterns comes in the 5 E's model that many of us use in planning our science lessons. The explore phase, for example, is really where we're making patterns visible. We're providing our students with many experiences. The green here are the cross-cutting, the places where this cross-cutting idea comes in, and the blue, to kind of align with the NGSS, would be a place where the practices come in. So as we're providing our students with experiences, they're planning and conducting investigations, this is one place where we're making patterns visible. And then we're identifying those patterns as they develop and use models, engage in arguments, and use mathematics and computational thinking. So exploring is really about identifying and making those patterns visible. And then the explain is when we really account for those patterns, try to come up with explanations or models that help us understand those patterns and why those patterns and maybe not other patterns. And then these same ideas come in again in the later stages in the 5 E's and elaborate, where we're providing some additional experiences, linking to the patterns they might have already identified, and using those explanations to explain new patterns that they might be seeing. This is a similar instructional approach that I like to use because it emphasizes patterns. It has a lot of similarities to the 5 E's. The question stage is similar to the engage, and then there's exploration and investigation followed by explanation. But what I like about this one is that it really makes explicit the connection to EPE, where we're doing inquiry and where we're doing application. And it also makes very explicit the role of patterns, exploring patterns, having students talk about their ideas about the patterns that they're seeing, students explaining the patterns, and then learning about the scientific ideas that explain those patterns. So this is just sort of another way to represent the ways that patterns are part of the inquiry and application teaching that we are engaging in. So let's take a look at some really specific examples. I have an elementary and a middle school and a high school example. So here's an elementary cross-cutting concept that students will be using patterns to understand the world around them, the observations they've made. The patterns can be used to describe these experiences, and they can be used as evidence. And a performance expectation that's linked to that is this one about sound, that students will be able to conduct an investigation to provide evidence. Here's the link between the pattern and the practice. That vibrating matter creates sound, and that sound causes matter to vibrate. And so the thing that's interesting about this performance expectation is that this disciplinary content right here is actually a pattern. So the students are learning the patterns in this example. And so again, I'd go back to the EPE table that I used. Here's the patterns that we want students to think about, to know and be able to use. And then we can ask ourselves, so what kinds of experiences can help our students see those patterns? Here's just a few types of things that young students can explore to begin to see how things that make sound vibrate, and that things that vibrate make sound, using rice drums, where you put a little bit of rice on the top of a drum. You hit the drum and you can see that the rice bounces up and down, or putting tuning forks in water. And then thinking about how vibrations can make other things vibrate. You can put a tuning fork near ping pong balls and watch how, without touching the ping pong balls, the tuning fork makes the ping pong balls vibrate and move around. And so from these experiences, then we can really help students articulate these patterns. And these patterns then can be used to come up with an explanation or an answer to this driving question about how we hear sounds. Here's a middle school example. The cross-cutting concept for patterns is that patterns in rates of change could provide information about the natural and design systems. So we talked about that concept a little bit earlier. A performance expectation that is linked to this concept is in life science that students can construct explanations for common patterns of interactions within different ecosystems. So these are patterns like predator-prey relationships, or symbiosis patterns, mutualism, commensalism, parasitism. Here is a graph that shows some of these types of relationships. This is data from Isle Royal up in Lake Superior, where they've been tracking the population of moose and wolves over a number of years. And if you look at this, you can see a couple patterns in this graph, and I've put them here on this EPE table. You can see that the populations of the moose and the wolves cycle. That there's up until 1985, there was a kind of predictable pattern that the population of the wolves, the cycle followed the prey, the moose. As the moose increased, then the wolves would sort of lag behind, but they would increase as well. And then when the moose fell off, the wolves also fell off. But then you might have noticed that in 1985 there was this real crash in the wolf, and the moose population spiked. So having students really look at those graphs and think about each of those points on the graph is an observation that helps us see these changes in populations over time. And we can also then ask a question, well, what happened in 1985? And the scientists, they were just as curious, wanted to be able to explain what was going on, and they were looking at lots of different possibilities, and the one that became rather intriguing was the introduction of parvovirus to the island, probably by people bringing their dogs to the island. And that decimated the wolf population, and then the moose population increased. So we can really use this to help students see these patterns in the ways that organisms interact in ecosystems. And then finally, a high school example. Patterns cross-cutting concept is that empirical evidence is needed to identify patterns. So here's an earth science example of a performance expectation that students should be able to construct explanations using a theory, so that's the practice. 4 patterns in general trends, there's our cross-cutting concept coming in, of the ages of both continental and oceanic crust. And so this is the kind of disciplinary core content. And you can go back to a graph or a map to see the data that let us see where our younger crust and older crust is located. We can put that map that I just showed up against a plate boundary map, and we can begin to see that the youngest crust is located along plate boundaries. and the older crust is located further from plate boundaries. And we can explain this using plate tectonic theory to understand where the volcanoes are located and the role that volcanoes play in producing new crust. So I was trying to give you examples across the grade levels and across the discipline of how we can emphasize patterns and help students really understand the patterns that hold the experiences and the explanations together. So kind of in summary of the main points that we've talked about here this evening, the patterns support the development of scientific explanations, and that we want to use patterns to help students, to support students in understanding core concepts. The patterns need to be visible in order to help students make those connections. We need to engage students in science of science. In order to do this, we need to engage them in using patterns as part of the scientific practices. And then that the cross-cutting concepts about patterns are built across grade bands and disciplinary content. So kind of our final reflection here is to think about in what ways might you use the EPE table to help you think about teaching about patterns across content areas. And then how is thinking about patterns and the patterns cross-cutting concept helps you think about your own teaching? And do you have any more questions?
Great, thanks, Kristin. Let's look through here. I want to just first reflect on one thing I had been thinking about. It was just looking at that pyramid and the issue of, you know, observations, evidence down at the base, and how you need to have a lot of those pieces in order to find patterns and in order to find explanations, and how, you know, we can sometimes, or I can think back to my own teaching, sometimes we throw out one or two examples and we expect students to gain an explanation just from that little amount of evidence, and how that, you know, we really need to go and provide a preponderance of evidence in order to help them see these patterns. So one question that's coming up here is, do you have any advice in terms of addressing patterns with ESL or ELL classrooms or students in intermixed and regular mainstream classrooms?
Well, I think the ideas are still the same, but maybe the ways in which we make those patterns visible, relying maybe a lot on the visuals, to help the students see the more grade similarities and differences among objects or phenomena, and then in the later grades really using graphs and charts to and take the time to help them see those patterns. And then it is also a great opportunity then to have them practicing use the new languages that they're learning, English that they're learning, to talk about the patterns that they're seeing.
Great. I saw one comment here that I thought was interesting. This idea of posting a large chart where a class can track experiences and identified patterns as lead to working as a group to develop explanations. Have you ever tried anything like that, Kristin, or how do you think that would work?
I really like that idea. I think that it really helps the students track of what they've been doing. It really kind of moves experiences from being fun, hands-on, fun activities, which they might think are just fun activities, to really helping them see why they might have done these activities and what the patterns are that help them connect those activities to those concepts. And I also like the idea of helping using it to help the class come up together with the explanations.
That's great. I see a comment here from Lauren that I think is something that a lot of teachers struggle with, and one thing I'd point to Lauren and others folks who have this question is to go and take a look at the web seminar we had last fall about students developing models. But Lauren asks, how do you get the kids to form their own explanations? Usually the teacher supplies the explanation part of the EPA to save time. I would think that research would have to be done by students to get the explanation step for some concepts. And what are your thoughts on that aspect?
Well, I think there's a couple things that I think about. One is that the next generation science standards are really helping think differently about teaching, and so it might mean taking more time to help students think about and construct the arguments, test their ideas in order to explain the patterns they're seeing. But at the same time, I also think that there is a role for providing some scientific ideas after students have identified the patterns, because I think that the type of inquiry that scientists engage in takes place over, as the plate tectonics example shows, and that took over 100 years to really develop that idea, and we don't have 100 years in our classrooms. So it's not like we can never provide the ideas, and it's not like we necessarily should expect that our students are going to discover all of the scientific content just by engaging in experiences and looking for patterns. But I think when we have an idea, an understanding of the role that patterns play both in supporting explanations and in helping students learn those explanations, learning that content, that we can engage in the practices strategically, and also strategically help them understand the explanations for the patterns that they're seeing.
I think that's a great point. It was something I'm reminded of, that I really didn't want to think that my physics students would be able to figure out in a matter of 3 or 4 months what it took Isaac Newton, 3 or 4 decades to figure out. Something I remember thinking.
Right.
They had one question here, which I'm going to suggest that maybe you just could answer in the chat window, of asking if any published works that we can further reference. If you have some links you want to send people to, if you want to put that in there while I go on and point some people to some things in a few minutes about NSTA resources. But go ahead. Do you want to say something?
I was just going to say that there is a resource, and I'll post it here right now, in Science and Children, that summarizes a lot of what I talked about today. So that's one place you could look.
Great. Thanks very much. And so I think we're on to rating your learning. And I'll let you, Bryn and Kristin, you two take care of that slide.
Thanks, Ted. And before we do move on to our final section on NGSS resources, we'd like to get a look at what you thought about rating your learning today. So just like we used the clip art at the beginning of the presentation, you can now select a piece of clip art to stamp in the box that accurately reflects where you're at there on the 3 columns. And Kristin, this is great. It looks like everybody's out of the still unsure box. Nice job.
Excellent. I like to see that.
Thanks everybody for putting up your stamps, and we'll go ahead and move on to Ted's closing.
Great, thank you everybody. Sorry to advance here on you all. Obviously, a thank you to Kristin. There's her contact information. We'll make sure you see that again. But I want to point out that you're looking for more information around NGSS. You can find it on the NSTA website. There is a link right in the top right corner of the NSTA homepage that will take you to our specific page dedicated to NGSS, or you can go directly there by just typing nsta.org/NGSS. I want to also note that we've got one of our community forums specifically dedicated to the next generation science standards, and that's a great place to go to continue some of the discussions that you've been doing in the chat today. Happy to see such an active and interested group. We've talked a lot about the framework. I want to mention, again, you can get the framework at the NSTA website. You could also get a book we've prepared, the NSTA Reader's Guide to the Framework for K-12 Science Education. We've had also a number of journal articles about the framework and NGSS, including an article about the cross-cutting concepts overall to take a look at. I think it was Rick Duschel who wrote that. We know the standards are coming out late March, is what our expectation is, which means that San Antonio, Texas will be the place to be in mid-April to learn about NGSS. I hope you all can come out there and see it. We've got a number of sessions, and you could basically spend all day, every day, learning something around NGSS if you wanted to at San Antonio. I know it's what I'm planning to do. We've got some upcoming web seminars on cross-cutting concepts. Our next one, I should say, 2 weeks from today, is about cause and effect, and later in March we've got one on scale, proportion, and quantity. I know our presenters for the scale workshop are actually here in the audience tonight, so tip of the hat out to those folks, and see down the line there is where the rest of those are. They'll all start at 6:30, and also just point out that, again, you can see some of our earlier web seminars and get to them from the NGSS page on the NSTA website. Archives pointed out, we've got runs of practices, our pieces in the last few we've had, and coming up, all of those are available at the following link. And new, and we're very excited about, a set of short courses around NGSS that we're starting up. These will be a series of web seminars on particularly high interest topics. Paige Keeley, if you don't know her, she's a former NSTA president, author of the Understanding Student Ideas series, author of Curriculum Topic Study, and she's going to be talking about formative assessment, which I should mention she's also written a book about formative assessment that you can see, and that will be coming up in April, in early May, and then later on in May we have a series by Kristin Gunckel as the main presenter from the Boston Museum of Science, also involved in the Engineering as Elementary curriculum. So for those, please go ahead and look into registering for those. Registration just opened literally today. And with that, I'll pass things back to Bryn, and thank you all for being here tonight.
Thanks, Ted, and we would like to take a moment to thank you and to thank our featured presenters tonight, Kristin Gunckel, for presenting such a fantastic program. We'd also like to thank everyone for your interaction and participation this evening. We would also like to thank the sponsor of today's web seminar, the Carnegie Corporation of New York. And a thank you to the administration of NSTA for their support for web seminars. Here's a look at our upcoming programs. You can register for these by going to the link there at the bottom, learningcenter.nsta.org/webseminars. And we'd like to thank everyone for your participation tonight. We'll see you again on another web seminar.